Now go. Welcome to the January 2026 indoor meeting of the Raleigh Astronomy Club. Dr. Shull, would you like for questions to be at the end or ask you at the time as you're going through, sir? Okay. Because we have this statement here and I just want to make sure. So we want to say that you can ask questions as we go through, but please urgent questions as you go through. And maybe if you've got other non-urgent questions, we wait till the end. Okay. Put your questions in the chat for the Zoom participants. Okay, so we are in a different room tonight than we normally are in the basement. And so everybody knows the exits when you go out the door on the left. Watch out for room hazards. We got lots of wires and cables and books. Yeah, there's no projectors. Sorry. Okay, who's my CPR certified? Anybody? Okay, I got two of you. Okay, if something happens to multiple, go for the co-chair first. Okay. Okay, who's my caller? Susan's my caller. Okay, fire equipment is right over there. So if somebody sets Dean Herring on fire, that's how you put him out. Okay, so I don't have a drawing for this room. I've asked, but we don't have one yet. But yeah, an emergency drawing to get out the door. But just head out the door and go down the stairs. Okay. Oh, crap. It's on the right over there. Yep. Okay, we're asking everybody that's in the um, Zoom chat, Zoom meeting to please be aware of your surroundings. Get up and move around sometime. We have a bunch of upcoming events, as you guys can tell. I'm not going to drain the slide. We are going to speak real quick here in just a second about astronomy days. Stephen is not here, but we'll talk about it. We're going to get Anna to not attend this. What? Okay, we'll go over it in a second, but yeah, I'm glad y'all pointed that out. The astronomy days are the 23rd and 24th. 24th and 25th that I have is the 23rd. We all good? You can edit it right now if you want to. Okay. Asking Anna not to go to First Fridays, please, because she always brings the weather. Oh, okay. Are you out of town on this one? Okay. Anyway, we're going to go through astronomy days for Sir Chris. Yeah, okay. So I can't type 23.
So who's right? Uh, that feels great. Okay. Okay. Most of the stuff information you already know about, and was it the theme this year is Passport to the Moon? Throwing that in here there right now for all the imagers who may be in this room or maybe on Zoom. I already have some of them who have sent me their moon images, but I would like to make a slideshow of moon astro images that you guys have taken over the years, and I'll be putting that over at the RAC table display. So, but anyway, yeah, those are exhibits right there. Astrophotography, RAC table, very good. RAC table, as the astronomer. Telescopes on display and solar observing. And there's a QR code there if you want to check it out really quick. It's pretty much the same information I just gave you. Okay, next slide. Okay. So some particulars and details. Exhibit descriptions are on the registration page. If you volunteer for more than 2 shifts, lunch will be provided by the museum for you. Okay. And I think it will actually be in this room. It's usually in this room. So, but one thing that I want to make clear is you do not have, because this I don't know why, but it just happens. It's almost every year. You do not have to sign up for the same exhibit twice. I mean, we even have a category that is not on among the previous slide that are called floaters. So if you want to be a floater because you don't know exactly which exhibit that you feel most comfortable with, you can come and just sample them all if you want. Or if no, the biggest point of our floaters is so that they can just assist where volunteers are a little bit thin. Okay, so but anyway, as it was said just earlier, on the 23rd, the Friday before the weekend of astronomy days, we will be doing a setup from 5 p.m. to 7 p.m. here at the museum. I do not have the full details of what that exactly looks like. I'm sure it's going to look pretty similar to what it has in previous years. So the museum will be communicating with me, and we'll have those details for you as soon as possible. So what I would like you guys to do is that it also says please register preferably by Monday, January 12th. Yes, that's next Monday. Carrie has wants to get the ball rolling really fast as far as us turning in all the volunteer information. And what's up? Okay, so the question is, if you register or if you want to, don't know if you can attend astronomy days or volunteer for astronomy days, but you will help if you can be here. Just go ahead and register anyway. Uh, the museum and RAC surely will not penalize you if you can't make it. So, so it's okay. Yeah. So, oops. Here we go. So anyway, but yeah, if you can, try to register by this Monday, and because I'll be turning in a lot of information for Carrie. She said that throughout the rest of next week, I can also keep turning in uh, any late stragglers that are made their decision with whether or not to volunteer. So, but as far as the people that have signed up so far with those 4 exhibits, we especially need help on Sunday. That is where volunteering is really thin. I think on the next slide, we have a look at it. So this is what we have signed up so far. So everybody in this room and everybody on Zoom who have already signed up, I am very happy that you have done so. Right now, if you look down at the floaters right now, uh, we're running really thin, especially on Sunday. But if you don't know what you want to do, you can sign up to be a floater, and we can distribute you to wherever station that you feel most comfortable volunteering in. Okay. Telescopes on display especially needs help on Sunday. And oh, another question. What's up? Okay. Yeah. So that's yeah. No, you do not have to be a Nobel laureate in astrophysics or just physics anyway. I don't know if there is one for astrophysics. I wouldn't think so. But anyway, in physics to be able to help out in astronomy days. If you come to each exhibit, there will most likely already have been somebody there who has volunteered previously before. You're just going to interact with the public, and if they have any questions about what each exhibit is about, if you don't know the answer, there's probably going to be someone else there that does have the answer to it. Okay. Yes, sir. Okay. The question is, hold on, say that again. Okay. So, yeah, bringing up telescopes on display, especially on Sunday where we need the most help. What's involved in that exhibit? Now, I'll go ahead and tell you right now, 2 things. If you're the type of person who is very proud of their setup, like I am, and you want to show off exactly it's not really proper of me to say this, how much money you spent on your setup and show how elaborate it is. Sign up for Telescopes on Display, and you can really show the bells and whistles of why your equipment has made you so successful in amateur astronomy, whether it be an imaging setup, you can bring an imaging setup, or it just be a purely visual setup with very expensive eyepieces, right, Jim? Yes. Okay. So, so anyway, so that's what's involved in telescopes on display. Now, the second part of that, what I was going to get to as far as telescopes on display, what's involved there, if you actually cannot bring your own telescope, but you would like to work telescopes on display, the the loaner program will bring some scopes for that exhibit. And if you know anything about Dobsonians or Newtonian telescopes, there will be one of those there. And I need to approach Yvonne, but I'm going to see if we can also get a Schmidt-Cassegrain telescope there. And again, if you can compare and contrast the differences between those two telescopes, you're good to go. The public will. That's more than enough information that just a regular member of the public would want to hear. Yes. Yeah, so things are way different as far as location for all the exhibits this time around, with the exception of astrophotography. Astrophotography is going to be at the same location. So the question was, where are all these exhibits going to be? So not for right now. I'm sure it's been finalized, but Telescopes on Display is going to be really close to the WREL Theater. Out front of that, off to the side, of course, not right directly in front of the entrance there. It used to be there a long time ago, and so they're putting us back there. And then let's see, astrophotography take place. RAC table, Ask the Astronomer is going to actually be over at the ticket counter, or next to the ticket counter, going towards the Marine exhibit hall. Okay. Now, again, this is in the NEC. Okay, not the NRC, the newer section of the museum. This is back at the older section of the museum. That's where the entrance is right across from the History Museum. And in the north, there's the Legislature Building. In the south, there's the nice, pretty Capitol building. So that's the building that we're going to be in this year. And but solar observing, that's probably one that's really going to have a dramatic change in location. It's actually going to be, well, in this room, we're here on the fourth level of the museum. It's actually going to be on this floor, but out that way. For everybody here who's here in person, that's where I'm pointing. so it's going to be on what's called the green roof. Okay, so that's a little open area. If anybody's familiar with how we volunteer over at the Willard, it's about the same kind of size area. Okay. Yeah, because you've already been registered for your own exhibit. You're running your show independently. Yeah, so Frank brought up just letting people know that will be all types of telescopes there, but which is what I said earlier. But what Frank brought up, they will be different sizes. So you'll see small ones, you'll see big ones, and whatnot. And we're going to try to have something out there for everybody to actually use the optics and observe. Hopefully, a crater that's been mounted on the wall. Okay. Anyway, okay, my time is short now, or my time is up now. So if there are any questions, just email the announcement section or the I guess membership chat group or members chat groups IO, or let us know on Discord if you have any questions. But there was the QR code. Just go to rackpolyastro.org and please help us out. Register for Astronomy Days. Thanks.
Come on, feel free. Okay, tonight's presentation, Dr. Michael Shull. We made it really, really short for introduction. Professor of Astrophysics at the University of Colorado, adjunct professor of physics and astronomy at UNC Chapel Hill. Got your BS in physics at Caltech, sir? Yeah. We got your Bachelor of Science in Physics at Caltech and his PhD from Princeton. So, without further ado, hand it to you. It will take just a minute to switch you over.
Do I need to hit share? Oh, I'm there. Okay, well, let me hit. I thought I hit it. It's not on.
Right.
Okay. Yeah, that's working. Okay, well, thanks for inviting me. I'm looking back, this is the fourth time I've spoken to you all, usually about things much farther away, galaxies at the edge of the universe, quasars, things like that. But tonight, I'm going to talk about some very recent work that got a lot of publicity. Those of you who get Sky and Telescope, December 11th, Jan Hottenbach wrote a very nice article about our work. One aspect of our work, which is that two stars in the Great Dog, Canis Majoris, swept by our sun 4.4 million years ago. He rounded it up, 4.5. But the punchline at the bottom, two winter stars, so you can see them tonight, left their mark long ago on the gas clouds around the sun. And at the end of the talk, I'll talk about habitability, what that might have done to influence life on Earth. So there's an interesting connection there. Okay, well, I'm among people who know more about the sky than I do. But in the Big Dog, Canis Majoris, are these two stars, one in the front leg and one in the rear leg. Below Sirius is Beta Canis Majoris. It's got the Arabic name Mirzam. And on the bottom leg is Epsilon Canis Majoris, also known as Adhara to the Arabs. If you had ionizing ultraviolet light in your eyes, those would be the brightest stars in the sky by far on Earth. They're both what we call B-type stars, and there I put the temperature. The surface temperature of the sun is about a little over 6,000 degrees Kelvin. These are 21,000 and 25,000, so pretty hot. That's why they put out a lot of ultraviolet light. And I should say, this paper that came out back in December, Rachel Curran, the second author, just graduated from University of North Carolina, Chapel Hill, in physics and astronomy. She decided not to go into graduate work right away. She's working up at the Applied Physics Lab up near Baltimore. A really good job. They pay very well too. So she's enjoying life. Okay, so here's a little sketch that I made for a talk this summer. So today, these two stars are down here, Epsilon and Beta. They're at 124 parsecs away or 150 parsecs. That's 400 or 500 light years. So they're pretty far away. And they're still pretty bright. But if you track their velocities back in time, which I've done here, these red lines, if you go back 4.4 million years ago, they passed by the sun within about 30 light years. And of course, being that much closer, they were really, really bright. If you go back somewhere in between, when the famous Lucy skeleton Australopithecus lived in Africa, those primates, if they would looked up in the sky, they would have seen the brightest stars, not Sirius, but these two, Beta and Epsilon CMA. They would have been 5 or 6 times brighter than Sirius is today. So really bright. Okay, so one of the things I want to leave you with the impression of is that we, the sun, the Earth, the solar system, live in a bubble. Other than these little clouds nearby us, we are in a very large cavity from side to side, maybe 300 or 400 light years across. It's called the local bubble or the local hot bubble because it's full of hot gas that was left by supernova, by exploding stars over here in Scorpius Ophiuchus. That is an association of massive stars, O and B type stars, and about between 10 million years ago and a few million years ago, they started popping off. And we think there's been maybe 10 or 20 of these stars blow up, and their shock waves, their blast waves, created this cavity, a very low density gas plasma, because it's all ionized, It's about 1,000,000 degrees Kelvin, which is quite hot. So I'll be talking more about the effects of this hot bubble later. You can see it's sort of oblong shaped. It's not round because the gas around it had very different densities. So the blast waves blew out in some directions more than others. And I want to call your attention to this little place down here. We call it the Interstellar Medium Tunnel, or ISM tunnel. And that figures in why these two stars, Epsilon and Beta Canis Majoris, are so bright in the ionizing EUV. They're down here, and they're shining their light through this tunnel to Earth. The Pleiades has a little bubble around it. There were a lot of stars that were hot, and some of them blew up, made a bubble there. And there's some others over here that I won't talk about today. Okay, so here's a sketch made if you had X-ray eyes of what the bubble looks like. This is in galactic coordinates. So the Milky Way disk plane cuts across horizontally in this picture. And the sun is at the middle. Over here is Orion, and over here is the Gum Nebula, another supernova. The bubble is all in gray. Here's the tunnel that I told you about. And it blew out to the top too. So everywhere there's a weak spot in the gas, not a high column density of interstellar gas, it's kind of like a hernia. This high pressure pokes through. And so we have an interstellar hernia going on, one out this way toward Canis Majoris stars, and one up toward the North Galactic Pole. And this is glowing hot in the X-ray. Million degree plasma radiates mostly in the X-ray. So this has been actually mapped out. These are real pictures taken by X-ray telescopes up in space.
Do you know why the area there is very dark?
Which area?
Below Orion.
Oh yeah, that's interstellar gas clouds.
Below.
And below it, yeah. These are all interstellar gas clouds, and I'll be talking about that more. But since you brought it up, it's a good time to say why that's important. Interstellar gas, if it's atomic, cold, has hydrogen and helium in it. That absorbs X-rays, and that absorbs the hydrogen ionizing photons. And so if you have a star down here, it may be really, really bright in the ionizing ultraviolet, but it can't get to the sun because that blocks it out. It's like dust clouds, same thing. But it's the hydrogen and helium that's doing the absorbing. Okay, now moving in a bit closer. I think everyone knows about the Voyager satellites, which were launched back in the 70s. They were launched to try to see and get out of the solar system into the true interstellar medium. Well, the sun has a wind, a very powerful wind, and it has blown a small bubble out at about 100 astronomical units, 100 Earth-Sun distances. That's called the termination shock. And then beyond that is the heliopause, where the interstellar medium is flowing into the solar system. So in the frame of the sun is actually moving very fast. The sun is moving this way to the left of the screen, and up to the top, I converted 26 kilometers a second to human units. It's about 58,000 miles an hour. Yeah, that's really quite fast. That's supersonic to the interstellar medium. Okay, that's why there's a shock wave. The sun is moving to the left, so if you put yourself in the sun's frame, the interstellar gas is sweeping into us. Okay, well, why is this important for habitability? Well, this solar wind and the magnetic field that goes with it shields us from a lot of cosmic rays. Okay, cosmic rays are not good for humans and any forms of life. They can ionize, they can create tissue damage, they can create DNA damage, they can mutate. So the fact that we live in this bubble with a magnetic field and a shock shields us from all the cosmic rays coming in from interstellar space. Some of them get through, but nowhere near what it would be. So this is called the heliosphere. The Voyager spacecraft has now gone through the termination shock, and it's out in here, out in this heliopause. One of them going this way to the top, one of them coming that way. The other one that you might have heard of, the mission that went to Pluto called New Horizons, is about to cross this termination shock in the next few years. It's out at around 64 astronomical units. You had a question. Are they? Oh yeah, they're still moving. They were launched at a very high speed. They're slowing down because of the gravity of everything inside the sun, but they're still moving, and they're out here. One of them is showing signs of not being able to communicate so well, but so far we're transmitting. The other thing that I want to say, the New Horizons spacecraft, which passed Pluto at 39 astronomical units, it's out at 64 AU. That's about 6 hours light travel time. So if you send it a signal, it takes 6 hours to get there and another 6 hours back. That's light travel for you. I better move on. Okay, so here was the picture that I sent out to everyone. Dana showed it at the very beginning. I'm going to repeat what I just said, but now in this pretty picture, which one of our former graduate students, Seth Redfield, put together. Here's the sun, and it's moving this way at 58,000 miles an hour. This is in galactic coordinates. So over here, L equals 0, galactic longitude 0, that's toward the galactic center. So that way, 26,000 light years away, is the center of the Milky Way. Okay, this way, longitude 90, that's the way most stars around the sun are moving. They're going around the galaxy in roughly circular orbit. So you can see the sun is racing a little bit inward toward the center and a little bit with everything else going with it. Okay, now this is the local interstellar medium. This light blue, local clouds, etc., are these wispy clouds that I talked about at the beginning. And they shield us from a lot of the ionizing radiation right now that's coming to us from these hot stars. This interstellar tunnel is down this way. So epsilon and beta CMA are down that way. But some of their light gets through and gets to the sun. Their ionizing photons gets through. And that's what I'm going to talk about later in the talk. Here's our nearest neighbor star, Alpha Centauri. That's 4.3 light years away. Here's Sirius over here. That's about 8 or 9 light years away. The Hyades cluster over here, all the other ones that you know about. And I think that's all I need to say about this one. But I'll be coming back to this in a little bit.
So are we about to pop out of that bubble? Of ultraviolet radiation coming from those
You just stole the punchline of the. No, it's good. You asked the right question. We are. I mean, it's obvious, and you can see the way the artists do. This is an artist schematic, but you can see we're headed this way, and in anywhere from a few thousand to maybe 10,000 years, we're going to be out here and get a big dose of radiation. So, bingo. How what? In how many years? A few thousand years. Between 2,000 and 10,000. We don't know quite for sure. As I said, this is an artist schematic. But hopefully our civilization will still be around. The countries we know and love today may not be around. But...
The more planetarium, with the whole inner part of the solar system and that little light ring around the planetary machine, and Pluto at the very outer edge of the whole theater, the first star, Alpha Centauri, would be down near Texas.
That sounds about right. Yeah, this is the nearest star. This is 4.3 light years. This is 8 or 9 light years. From side to side here, well, you can see it here, 20, 10. This is about 30 light years across. So the local clouds, our local neck of the woods, is about 30 light years around. Once you get beyond that, this is kind of your question out here, now you're in the local hot bubble, that hot plasma hitting you, and you don't have the hydrogen gas here shielding you from those ionizing photons. And that's what a lot of a talk's going to be about. Okay, so here this kind of summarizes what I've been telling you. Another schematic from a paper in the Astrophysical Journal a few years ago We are here. If you go out 140 parsecs this way, you get to the Taurus association of hot stars. If you go a similar distance over here, you get to the Scorpius Ophiuchus, the stars that blew up and made the bubble. Everything else is this hot cavity. And I call it the local hot bubble. It's about 1 million degrees Kelvin, and it's a very, very low density. The main stars that ionize it, and I'll come back to this at the end of the talk, the two stars in the big dog, Beta and Epsilon Canis Majoris, they're down here. There are 3 white dwarfs that are also contributing. They're even hotter. They're up at 50,000, 53,000 Kelvin. And the hot bubble. So the title of the paper that we published in December was The 2 B stars, the 3 white dwarfs, and the hot bubble. Someone can make a movie out of it. Okay, and then just to wrap it up for the amateur astronomers here, if you go out at night in the winter sky, if it ever clears up, you can find Sirius, come down the front leg, that's Beta CMA, 490 light years away today. Come the left leg, Adhara, Epsilon CMA, that's a little closer, 400 light years away. That's today. But again, go back 4.4 million years ago, these stars are moving, the sun's moving, they're moving, they pass by the sun within 30 light years. And of course, Orion is way up here. Okay, so I'm going to give you a little more of the astrophysics behind this. This is called the Hertzsprung-Russell diagram, if you've read the books about it, or color magnitude. Instead of magnitudes, I've put logarithmic of the luminosity. So this is a log scale. 1,000 times the sun, 4 is 10 to the 4th times the sun in luminosity, 10 to the 5th times the sun. These are really, really luminous stars. The brightest, most luminous stars, most massive stars that we know of. Along the horizontal axis, astronomers will plot color. Astrophysicists like me will plot temperature. And this is in kilokelvin. So this is 30,000 Kelvin, 20,000 Kelvin, 10,000 Kelvin. Remember, the sun is 6,000 Kelvin. So these are hot stars. And these are their masses. 7, 9, 12. So as far as we can tell from doing the colors and really figuring out how luminous these stars are, here they are, Epsilon CMA, Beta CMA. They're about 20,000, 30,000 times the luminosity of the sun. So they're really, really quite luminous. They started out their life on the main sequence at somewhere between 12 and 15 times the mass of the sun. So they're big guys. The most massive stars we know of are way up here at maybe 100 solar masses. But these are the ones that we're going to talk about today. Okay, a couple of diagrams of spectra that kind of explain what we did and why these stars are so bright, so luminous in the ionizing continuum. These are not black bodies. These atmospheres of hot stars have a spectrum that rises into the UV, into the ultraviolet. There's 1,000 angstroms, and then they plummet at 912 angstroms. Why 912? 912 angstroms is the wavelength of photons in the ultraviolet that will strip an electron off of hydrogen. It'll ionize it. So the fact that the spectrum drops, it plummets right there at 912, is because the atmosphere of the star has some hydrogen in it. It hasn't ionized the hydrogen entirely. And that's just enough to put a notch there and knock out or absorb out that light. There's another notch at 504 angstroms. That's the helium, stripping off the helium electron. So these stellar atmospheres, and we did models using a state-of-the-art code. These tell us how much hydrogen and helium is absorbing the light just within the stellar atmosphere. But then the same thing goes on in the gas in between, the interstellar medium. The hydrogen in the interstellar gas absorbs even more. And so that is really the gist of it. So here's real data. This was taken by a rocket flight at the University of Colorado, launched from Wallops Island, not too far from here, off the coast of Virginia. That's where NASA launches their rockets. And this was a graduate student's PhD thesis, Nick Erickson. Here's what he measured here on Earth, or actually above the Earth in the sounding rocket. There's the ultraviolet. Then he saw that big notch, that big drop in flux at 912 angstroms, and then a slow recovery. Okay, so the bottom line of this rocket spectrum is that epsilon and beta Canis majoris have a lot of ultraviolet that doesn't ionize hydrogen, but it plummets. That's good. That means that the interstellar medium is shielding us from those harmful radiations. So this is the portion of the spectrum that got through down to the atmosphere, slightly above the atmosphere of Earth, that can ionize hydrogen. Now, I should say this is above the Earth's atmosphere. Here on Earth's surface, none of this gets down. Anybody know why? Sorry. But what about our atmosphere? Which atoms are molecules? Ozone, oxygen, yeah. Ozone, the ozone layer you hear tell about that was kind of thinning out over Antarctica. That ozone, O3, is killing all this stuff. So again, that helps shield us. We get shielded by Earth's atmosphere. We get shielded by the interstellar medium. Okay, so we're talking a little bit about habitability. This is what Rachel Curran, my former student at UNC, did for her honors thesis. She took this spectrum that the rocket measured and then did some modeling of what these interstellar clouds would do if you undid the absorption. And so this is what the radiation outside the local cloud would look like. If you went out 20, 30 light years away, that's how much radiation would be getting through. This is a log scale. This is a factor of 10. So you can see it's boosted by factors of 10, 20, 30 once you get outside. So the local clouds, these wispy clouds of hydrogen, are taking this spectrum, this amount of flux, and knocking it down. That's the shielding that's protecting us. But you go back 4.4 million years ago, and we were getting a heavy dose. We weren't getting this. We were getting something way up here. Or the Earth was, not we. Okay, one more technical point. This is all part of a talk I gave up at a conference this summer. So I've mixed in some fun slides and some technical slides. But there's an anomaly that has been noticed that helium in the local clouds is more ionized than hydrogen. And that was hard to understand. Well, the answer we have found is that helium, the ionization cross-section of helium, is a lot higher than hydrogen. You can see hydrogen falls off like that with energy. This is the photon energy. Helium is higher to start, and it falls off less rapidly. So we were able to explain, or Rachel was able to explain, that the preferential ionization of helium from the local clouds is because there's a lot of high energy photons coming in from the hot bubble and these hot stars. So you're up here where helium is much more important than hydrogen. Okay, so now a little interlude for what might have been going on 3, 4, 5 million years ago. I need to tell you a little bit about what happens after a star on the main sequence, like the sun, ends its life. So the main sequence is this locus, this line, locus of points that tell you where most stars are born, and where they land on the main sequence depends on their initial mass. Okay, and I drew a little dividing line here right at about 10,000 degrees, or 8 solar masses. Stars above 8 solar masses end their life as explosions, supernova, and they leave behind a neutron star or black hole. NS, neutron star, BH, black hole. And I'll show you some pictures in a second. These explode as supernova. Stars like the sun, which are down here, don't explode as supernova. They puff up and become red giants. So in about 5 million years, our sun is going to become a red giant. And down in the core, which will collapse, it'll start burning helium. And then it'll swing over and be a horizontal branch star, go up a second time to what's called the asymptotic giant branch, or AGB. And then after that, it will probably become a planetary nebula. It'll puff off its atmosphere. It'll sweep by the sun and Earth and Mars and puff off and make a planetary nebula. Those of you who take pictures know what I'm talking about. These stars up here, these are the ones that we think ionized our interstellar cloud. Now, you remember I said beta CMA was about 21,000 Kelvin. So it would be right there. And no, I said that backwards. Epsilon CMA, 21,000. And beta CMA, 25,000. So those stars started out right here. And in a few million years, they're going to blow up as supernova. So that's a quick summary of stellar evolution. Much more you can read about on that in books. Now for the pictures. Now, we don't live anywhere near an association like this, but if you lived in the southern hemisphere, you know the Large Magellanic Cloud, LMC. This is the famous Tarantula Nebula, and 30 Doradus, the star cluster right there. There are maybe 1,000 of these massive stars down in there. Some of them have already started blowing up, but you can see what they do. They ionize the gas all around it. They blow holes and cavities. That's what happened to a much lower degree 5-10 million years ago when the stars in that Scorpio-Centaurus association started blowing up. They started blowing holes in the gas and heating it up through their shock waves, their blast waves. It's like hydrogen bombs going off in interstellar space, and it does this to the interstellar gas. Now, something closer to home is the Carina Nebula. And this is one that I've actually worked on. This was taken by the Danish 1.5 meter telescope down in Chile. You need to be in the south to see it. The Orion Nebula is somewhat like this, nowhere near as big, but the same thing. You've got lots and lots of massive stars. Here's a group of them. Here's another group of them over there. And you can see the cavities that they blow. So if you happen to think about the fact that there's stars and planets everywhere, and there's probably habitable planets around stars inside here, that's a pretty inhospitable place to live because of the blast waves, the hot plasma, the ionizing radiation from all these hot stars. Where's Eta Carina? Eta Carina is down in here. And this is the Keyhole Nebula. So all this area here is Eta Carina.
Harder than our sun.
That sounds about right. Yeah. It's a very, very massive star. Started out maybe 100, 120 times the mass of the sun. But this, from side to side, is maybe 1,000 light years. This is a much bigger, scaled up version of what went on around the sun. But I just show it because it's so lovely. Okay, individual stars when they explode. This is Cassiopeia A, a supernova remnant. This is a picture mostly taken with X-ray emission. This gas is several million, maybe 10 million degrees Kelvin. Right at the center is a point source in the X-ray, a compact X-ray source. That's the neutron star left over from the massive star that blew up. So it blew off its outer layers. This stuff here in, I guess that's kind of yellow-green. A lot of that is oxygen that was made down inside that star, and it blew it out into space. So the oxygen that we're all breathing came from stars like this that blew up, blew the oxygen out into space, and many, many other heavy elements needed for life, carbon, nitrogen, iron, etc. There's a little place where it broke through there, but that's a neutron star. 1680, we think, was when it exploded. This is a somewhat older star. There's no historical record of it, but as far as we can tell, from its size and tracking it back, this blew up around 2,000 years ago. SNR is supernova remnant. These are all over the Milky Way. These are blowing up in the Milky Way about once every 50 years on average, somewhere in the Milky Way. And again, you can see big empty cavity. Well, it's not empty, it's full of hot gas, but it's been blown out by the explosion.
Who took those pictures?
These were taken by NASA satellites, the Chandra X-ray telescope, that previous one. In fact, one of my former students who's on the faculty here at NC State, Kajik Borkovsky, works on those. This one here. So yeah, NC State's doing good work. In X-ray astronomy, they're a powerhouse. In fact, what they've been doing, this will be interesting, they come back in every 10 or 20 years and take another picture, and it's moved. You can actually see it expanding over 10 or 20 years. Okay, getting near the end, I want to just give you a flavor of what the X-rays look like and what's making them. This 1,000,000-degree plasma, it's got hydrogen and helium in it, but most of the X-rays that come to us in this ionizing photon band, here's 900. So there's the hydrogen 912 angstrom limit. Most of these X-rays come from heavy elements that were synthesized by the supernova. These are all iron lines, all this stuff up here. Magnesium, neon, more magnesium, more neon. So it's the heavier elements, not hydrogen and helium, but these heavier elements blown out from the supernova. And so what we did was calculate what a 1,000,000-degree plasma should look like at different temperatures, up and around 1,000,000 degrees. And there's a lot of ionizing radiation that comes at us from these heavy elements: iron, silicon, magnesium, neon. Okay, I think this may be the end of the talk. I wanted to show you a slide from the New Horizons spacecraft, this one that's going out past Pluto. It's now out at 64 astronomical units. That's, what is it, I think it's 6 billion miles, if I remember. Anyway, it's out there. It takes 6 hours to get back to communicate. But it's way far out away from the sun and all the inner solar system. And that allows us to look in the ultraviolet, and this purple glow is all ultraviolet radiation coming from this local bubble and the gas around it. Overplotted on that, these yellow spots are the 5 stars that I've been talking about. The 2 stars, Epsilon and Beta Canis Majoris, there they are over there. This is in galactic coordinates, by the way. So the Milky Way plane is horizontal, and the North Galactic Pole is the top, the South Galactic Pole down there. The other 3, this one, and that one, the other 3 yellow spots are those 3 white dwarfs. You may not know them. They're not that well known. They have names or numbers. Phage 24, HZ43A, G191. These are named for the astronomers that put their name on the paper. Gliese, G for Gliese, got his name on the paper. Maybe of interest would be how far away they are, and I didn't put that on here, but they're about 50 or 60 parsecs away. Okay, not as far as these, Beta and Epsilon Canis Majoris, but they're still nearby. This one is up at very high galactic latitude. So their radiation is pouring down on our local cloud. In 10,000 years, as we said at the very beginning, this is what you guessed, we're going to move out of that cloud. And now you don't have all the local clouds. That's what these lines are. You don't have all the local clouds hydrogen to shield us from their radiation. It's going to be a very, very hot place. Not only these stars, but the hot bubble that is going to keep the Earth's atmosphere not inhabitable, but it's going to be a lot different than it is today. There will be more mutations of species, plants. Certain plants will have to evolve to survive. Some can survive UV, some can't. I think, yes, that is the end. So glad to take your questions now and hear what you have to ask. Yes.
Right. These stars.
Yeah. In fact, the sun is the one that's moving. Yeah. We're still learning a lot about this moving jigsaw puzzle locally, but we're pretty clear now it's the sun that is the anomaly. We're racing. If I go back to the very beginning, our sun is the one that's racing out. And so if you go back 4 million years ago, the sun was down here, and that's where those stars are. But you're right, motion is all relative. Yeah. What is it? What? Lead to, yeah. Okay, so here's the sun, and it's moving that way. Down here is that local interstellar tunnel. If you go beyond that, it's a big interstellar gas cloud. All the dark spot here, dark patches, are hot gas. So if you look at pictures of the Milky Way, you'll see dark clouds. They've got gas and dust in them. That's why they're dark. So this bubble is expanding into a denser part of the interstellar gas. So I expect the bubble is slowly getting bigger. But this gas cloud here, these gas clouds are not the local clouds. The local clouds are all right in there.
So just thinking about initially at the beginning, you said that what this has or what this means that habitability here
Yeah.
on Earth. So, and that's great. I like the one from back where you were talking about where you showed where the stars were actually moving across the sun. So
Yeah.
was that roughly about 4.4 billion years ago? Then a moment of higher extinction rate here on Earth because basically we really didn't have that cloud
Yeah.
shielding us.
This is my little sketch of what the clouds look like. Yeah. Well, first thing that surprised me when I did this calculation almost 2 years ago, I was working on this star, Epsilon CMA. I took its radial velocity, how fast it's racing away, and tracked it back when it came by the sun. I got 4.4 million years. Then I did the same calculation for this other star, and I got the same number. So these must have been born very close together in a cluster, and the sun has been racing away from them. But if you go track it back 4.37, 4.4 something, and then you do the offset to get how close it came, you have to get the proper motion of the star. I looked that up, and that's what gave me this 9 or 10 parsecs offset. So 30, 35 light years was how it was a pretty close encounter. Massive stars don't usually come that close to us. Yes. That would help us in the extent that that you ionize and then you do what's called recombination. The electrons that you stripped off can get captured again, and it become neutral. So as the sun, as these stars move away, the sun is getting bathed by less ionizing radiation, so it's becoming more neutral. Neutral atoms absorb the ionizing photons, so making it more neutral is good for habitability. Yeah, you got the right sense.
Question from Zoom. Why is the sun's trajectory different from the gas that we are moving through? Like what?
Yes. Why is the sun's trajectory different from the gas that we're moving through? We don't really know, but the main thing is that most stars around the sun are moving up toward longitude L of 90. It's called the local standard of rest, but they're going around the Milky Way roughly in a circular orbit. The sun is an anomaly, probably because it was born in a different place than other stars and got what we call a peculiar velocity. 26 kilometers a second is sort of a peculiar velocity. But Other than that, I don't think we know for sure, but there are stars that are moving faster than the average. Yes.
Back, 4.1 years ago, reading archaeological highlights or changes that kind of coincide with that as the radiation.
Yeah, good question. This conference I went to this summer where I gave this talk, there were a lot of experts on that. I'm not an expert on that, but what I learned was very exciting. There are some hints of things in the ocean floor and in other places. Iron 60, the number 60 isotope of iron, which is probably could be created by supernova. So there is that in the deep ocean sediments that they measure. As far as humans and extinctions and things like that, I doubt that this would be a mass extinction like Chicxulub, the asteroid that hit 63 million years ago. It's not like that. It's more like a mutation, a gradual set of mutations. Someone asked me how long would it take to pass by? Well, you can sort of see by the time you're at 1.6 million years, you've gone quite a bit farther away. So I would guess it would be maybe a few million years each side of the closest passage. So that's a very gradual change in ionizing radiation. But as far as seeing anything in the fossil record of plants or species, I don't know of any evidence. Another question? Yes.
With those low densities, is there the atoms colliding for like supersonic versus subsonic?
Yeah. Yeah. Okay. So this is the solar wind. It's coming off at about 400 kilometers a second. So remember, the sun is moving at 26 kilometers a second. This is supersonic. It's even what we call super magnetosonic. The magnetic field is out here too, and you've got to be faster than a magnetic sound speed. It's called the magnetosonic speed, but it is magneto-supersonic as well. So this really is a shock, and that's been seen now by Voyager and also by New Horizons spacecraft. Actually, you see various shocks, little mini shocks, because the solar wind is coming out radially, but the sun is rotating. So the magnetic field is getting wrapped up in a spiral as it goes out. So every time you go over one of those magnetic field lines, it's like going over a corrugated rib, a speed bump, boom, 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 boom. So they see mini shocks all the way out, but the big shock is right here. And Voyager went through those a few years ago at around 84 and 92 astronomical units. And they're now way out into this heliosheath. And you asked about something else, about shock waves or magnetic fields? It's a collisionless shock, but that's where the magnetic field comes in. So since you asked, if this is a field line, think of like a rubber band, a charged particle is gyrating around it because of the magnetic force. Okay? This is plasma physics. And so as it goes out, it's gyrating around, but it's kind of stuck to the field line. So the fact that it's tied to the field line and another magnetic field line with other atom going around it come together, they talk to each other, they know about each other, they exert forces on each other, and that creates the shock. And it's called a collisionless shock. It's interesting plasma physics. Little sidebar, our country and Europe are trying to make controlled nuclear fusion work. And that's the kind of plasmas that they have to deal with because they're trying to contain it with a magnetic field. And they get these collisionless effects and instabilities in the plasma. Final questions from
We
Zoom.
have one more on Zoom. Do we know when we entered the ionizing gas that we're currently in?
Did we know when we enter the cloud?
The cloud,
Probably.
right.
Yeah. Well, again, just tracing it back, and these are just approximate distances, but these are, you can see, they're of order 10 light years. And from side to side, maybe 30 light years. I had a slide that showed those velocities converted to light years per million years. Is it here? Maybe I didn't have it. Well, anyway, I think if you take one of these stars, it's moving at maybe 20 or 30 light years every million years. So moving out of the cloud is much, go back to this picture here. Moving out of the cloud, going this way is probably quick, maybe 10,000 years, could be as little as 2,000 years. Coming in the other way, I would guess similar. Yeah, probably of order, we entered the cloud maybe 10,000 years ago, which is a wink in the eye as far as astronomers think. We think in million years or billion year timescales. But the bottom line is, in a few thousand years, we're going to get a heavy dose of radiation. That's the takeaway message. Sure.
From the artist's concept.
These little gaps here? Yeah.
Yeah, very long.
Well, the gaps here are, as I said and you said, artist's conception. That's still being debated heavily. Seth Redfield thinks there's a gap. A lot of us who have looked at the velocities of these clouds, these little blue arrows are where they're moving. You can measure their velocities from the Doppler effect. And you can see they're all moving in different directions. It's like little pieces of a jigsaw puzzle, but all moving different ways. So I'd be very surprised. Yeah. Oh, yeah. The cloud cover. Yeah.
So, but the question that would be is that you have a predicted gap, but is that actually this is going to collapse?
No, I think there's an awful lot of artistic license going on here. I wouldn't put too much stake in it. It could be, in fact, one group has written a paper that this is all one big cloud tied together, held together by magnetic fields. Again, magnetic fields are all over the place, and they're like almost like glue. They can hold the gas together. But what we do know is that once you get out here, beyond about 20, 30 light years, we know from measurements of stars beyond off the plot, you're in the hot bubble, you're into the hot plasma. That much we do know. The other thing that I could comment is that people ask, what made these wispy clouds? How did they get there in the first place? Probably the blast wave that came from the supernova up here in Scorpius swept through here a few million years ago while it made the bubble. And they compressed the gas. We don't really know. It's one of those fortunate things where we live, Copernicus showed we don't live at the center. We live out orbiting the sun. The sun isn't the center of the Milky Way. We're out orbiting the Milky Way. Well, we're fortunate to live within this wispy gas, at least for the last few thousand years. On that somber note, maybe we should call it a day. Okay, thanks.